Good day everyone, my name is George and I'm going to present to you Chapter 8, and Chapter 8 is all about right triangles. Of course, it is very important that we are guided of what to learn in this video. That's why please allow me to present to you the overview and the learning targets for this discussion. So let's start with the overview of this discussion. The first lesson is all about right triangle similarity. The second lesson is all about Pythagorean theorem. Lesson number 3 is all about converse of Pythagorean theorem. Lesson 4 is special right triangles. And lesson 5 is all about trigonometric ratios. Starting the discussion with lesson 1, which is all about right triangle similarity. In right triangle similarity, we are applying the right triangle similarity theorem. The right triangle similarity theorem states that the altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. Having here a red triangle, triangle A, B, C, with altitude C, D, the altitude divides the triangle or the original triangle into two similar triangles. These are triangle ADC or the smallest triangle. The other triangle is triangle CDB. And by right triangle similarity theorem, we can say that triangle ADC or the smallest triangle is similar to triangle ACB, which is the original triangle, and also similar to the next triangle or to the other triangle, which is triangle BDC. With the use of triangle similarity theorem, we can identify similar triangles just like what we did. For example, another example is triangle RTS with the altitude TU divides the triangle into two similar triangles, the triangle TUS, STU or STU, and triangle RTU. We can say that the triangle TSU is similar to the triangle RTU, the other triangle, and similar to RST, which is the original triangle. Corollary of right triangle similarity theorem. The length of the altitude to the hypotenuse of a right triangle is the geometric mean of the length of the segments of the hypotenuse. Having here an example by applying the corollary of right triangle similarity theorem, we have here, or we have to solve for x and y given the illustration. So we can see that the altitude divides the original triangle into two similar triangles. So we can have here the white triangle with the same measures repositioned, the red triangle with the same measures repositioned, and the original triangle with the same measures. So by then we can use proportions to solve for y. So we have here y is to 4 using the sides of the white triangle. Y is to 4 is equal to 5 is to y using the sides or the measures of the second triangle or the red triangle. With the given proportions, we can now solve for y. So to solve for y, we have to apply cross multiplication, and y times y, that will give us y squared, and 4 times 5 is equal to 20. Since we are solving for y, we need to get the square root of both sides. The square root of y squared is equal to y, and the square root of 20 is equal to 2 square root of 5. So the value of y is equal to 2 square root of 5. The same way, and with the same given and illustration, we can solve for the value of x using these three similar triangles. So we can now write the proportions. X is to 4 equals 9 is to X. So we used here the smallest triangle and then the original triangle. So X is to 4 is equal to 9, that is 4 plus 5 is to X. To solve for X is to apply the cross multiplication. So we will have X squared equals 4 times 9, that is 36. Getting the square root of both sides to solve for X, we will have X is equal to 6. In real-world connection, a roof has a cross-section that is a right triangle. The diagram shows the approximate dimensions of this cross-section. Find the height of the roof. So we will have here the diagram of the problem. We need to find the height or the altitude of the roof. Solution. First is we have to understand the problem. We are given the side lengths of a right triangle. We need to find the height of the roof, which is the altitude drawn from the hypotenuse. Second, we have to make a plan. Identify any similar triangles, then use the similar triangles to write a proportion involving the height and solve for h. So these are the triangles formed, the small triangle, the other triangle, and then the whole triangle or the original triangle. So these are the triangles formed with the same measures. The triangles are just repositioned. And by triangle similarity theorem, we can say that the triangle XYW, or the smallest triangle, is similar to triangle YZW, the other triangle, and also similar to the original triangle, which is the XZY triangle. So using the triangles or the similar triangles, we can say, as what we have mentioned a while ago, triangle XYW is similar to triangle XZY. We can now write a proportion using this YW. So that is YW using the smallest triangle is to ZY. So that is using the original triangle. That is equal to XY, the smallest triangle, is to XZ, using the original triangle. That's why we will have corresponding side lengths of similar triangles are proportional. So after that, we will have h is equal h is to 5.5 is equal to 3.1 is to 6.3, or h over 5.5 is equal to 3.1 over 6.3, and that is by the substitution process. So our h is here, the YW, and then the 5.5 is here, the XZ, the ZY, and then 3.1 is the XY, and then 6.3 is here, the XZ. Next is to solve for h by multiplying both sides by 5.5. So our h now is 2.5. So we can now say that the height of the roof is about 2.7 meters. Moving to lesson 2, which is all about Pythagorean theorem. Over 2,000 years ago, there was an amazing discovery about triangles. When a triangle has a right angle or 90-degree angle and squares are made on each of the three sides, then the biggest square has the exact same area as the other two squares put together. So we can see that using the illustration. It is called Pythagoras or Pythagorean theorem and can also be written in one short equation. So that will be a squared plus b squared, and that should be equal to c squared. That is Pythagorean theorem all about. A squared plus b squared is equal to c squared. The sum of the area of the two squares is equal to the area of the biggest square. The longest side of the triangle is called the hypotenuse in Pythagorean theorem. So the formal definition is, in a right-angled triangle, the square of the hypotenuse is equal to the sum of the squares of the other two sides. As an example is a 3, 4, 5 triangle has a right angle in it. So using the figure, we have here the area of the smallest triangle, and then the area of the other, the area of the smallest square plus the area of the other square is simply just equal to the area of the bigger triangle. So by using the Pythagorean equation, we will use 3, 4, and 5 as sides A, B, and C. So we will have 3 squared plus 4 squared is equal to 5 squared. So simplifying, we will have 9 plus 16 is equal to 25, and that's 25 is equal to 25. Now, why is Pythagorean theorem or Pythagoras theorem useful or important? First, if we know the lengths of the two sides of a right-angled triangle, we can find the lengths of the third side. But of course, you always have to remember that it will only works on right-angled triangles. For example, solve this triangle given the sides 9, B, and 15. So B is unknown, we need to solve for B. So we have to start with the Pythagorean theorem equation, the a squared plus b squared equals c squared. And then put in what we know. We know that a is equal to 9, and then c is equal to 15. That's why we'll have 9 squared plus b squared is equal to 15 squared. The next step is to calculate the squares. We will have 81 plus b squared is equal to 225. To solve for b squared, we need to take 81 from both sides to balance the equation. So we will have 81 minus 81 plus b squared is equal to 225 minus 81. So we will have b squared is equal to 225 minus 81 is 144. And to get the value of b, we need to get the square root of both sides. So b is equal to square root of 144 and b is equal to 12. Does the triangle given have a right angle? A triangle with measures of the sides square root of 3, square root of 5, and square root of 8. Thus a squared plus b squared is equal to c squared. Thus square root of 3 squared plus square root of 5 squared equals square root of a squared, 8 squared. And thus 3 plus 5 equals to 8? Yes, it does. Therefore, this is a right-angled triangle. Moving to lesson 3, or the converse of the Pythagorean theorem. For any triangle with sides A, B, and C, if a squared plus b squared is equal to c squared, then the angle between A and B measures 90 degrees. And the triangle is a right triangle. The converse of the Pythagorean theorem can also be used to check whether a given triangle is an acute triangle, a right triangle, or an obtuse triangle. For a triangle with sides A, B, and C is the longest side, if c squared is less than a squared plus b squared, then it is an acute triangle, meaning to say that the angle facing side C is an acute angle. For a triangle with sides A, B, and C is the longest side, if c squared is greater than a squared plus b squared, then it is an obtuse triangle, and meaning to say that the angle facing side C is an obtuse angle. For a triangle with sides A, B, and C is the longest side, if C squared is equal to A squared plus B squared, then it is a right triangle. That means angle facing side C is a right angle. For example, determine whether a triangle with sides 12 centimeters, 14 centimeters, and 18 centimeters is an acute, right, or obtuse triangle. Solution. Which is the shorter sides to be A and B and the longest side to be side C? So A is equal to 12 centimeters, B is equal to 14 centimeters, and C is equal to 18 centimeters. Using the Pythagorean equation, we will have A squared plus B squared is equal to C squared. Putting what we know, we have, or A is equal to 12, so we'll have 12 centimeters squared, plus B is 14, so we'll have 14 centimeters squared. That is equal to our C, 18 centimeter squared. So we will have, by simplifying, 12 centimeters squared, that will give us 144 centimeters squared, plus 14 centimeters squared is 196 centimeters squared, and that is 18 centimeters squared will give us 324 centimeters squared. Is 340 centimeters squared equal to 324 centimeters squared? No, 340 centimeters squared is greater than 324 centimeters squared. As you can see, the value of C squared is 324, and the value of the sum of the squares of A and B is 340 centimeters squared. C squared is less than the A squared plus B squared. Therefore, this triangle, or this triangle with sides 12 centimeters, 14 centimeters, and 18 centimeters is an acute triangle. Another example, determine whether a triangle with sides 8 centimeters, 15 centimeters, and 17 centimeters is an acute, right, or obtuse triangle. Solution. Which is the shorter sides to be A and B and the longest side to be side C? So A is equal to 8 centimeters, B is equal to 15 centimeters, and C is equal to 17 centimeters. Using the equation, we will have 8 centimeters squared plus 15 centimeters squared is equal to 17 centimeters squared, because our A is 8, our B is 15, and our C is 17. So we will have 64 centimeters squared plus 225 centimeters squared equals 289 centimeters squared. Is 64 centimeters squared plus 225 centimeters squared equal to 289 centimeters squared? The sum of 64 and 225 is 289 centimeters squared, and that is equal to 289 centimeters squared, which is the value of the C squared, meaning to say that the triangle with sides 8 centimeters, 15 centimeters, and 17 centimeters is a right triangle. Moving to lesson 4, which is all about special right triangles. So special right triangles, a right angled triangle, also called a right triangle, is a triangle with right angle or 90 degrees in it. So we are given an example of a right triangle and an illustration of two most commonly known special right triangles, the 45-45-90 triangle and the 30-60-90 triangle. There are also other types of special right triangles, the 3-4-5 triangle and the 5-12-13 triangle. But we will only be focusing with the 45, 45, 90 triangle and the 30, 60, 90 triangle. So what is a 45, 45, 90 triangle? A 45, 45, 90 triangle is a special triangle with angles measuring 45 degrees, 45 degrees, and 90 degrees. The lengths of the sides of the 45, 45, 90 triangle are in the ratio of 1:1 square root of 2. Having here the illustration, we can say that the ratio of the side is x is to x square root of 2. A right triangle with two sides of equal lengths must be a 45, 45, 90 triangle. Find the length of the hypotenuse of a right triangle if the lengths of the other two sides are both 3 inches. Solution. Step 1. This is a right triangle with two equal sides, so it must be a 45, 45, 90 triangle. Step 2. We are given that the both sides are 3. If the first and second value of the ratio x is to x square root of 2 is 3, then the length of the third side should be 3 square root of 2. Therefore, the answer, the length of the hypotenuse is 3 square root of 2 inches. Find the length of the other two sides of a right triangle if the length of the hypotenuse is 4 square root of 2 inches and one of the angles is 45. Solution. This is a right triangle with a 45, 45, 90 angles. We are given that the hypotenuse, or the measure of the hypotenuse, is 4 square root of 2 inches. If the third value of the ratio x is to x square root of 2 is 4 square root of 2, then the lengths of the other two sides must be 4, meaning to say that the lengths of the two sides are both 4 inches. Moving to 30, 60, 90 triangle or 30, 60, 90 special right triangle. By illustration, we will have the measure or the ratio of the measure of the sides. We have x is to x square root of 3 is to 2x. Another type of special right triangles is the 30, 60, 90 triangle. This is a right triangle whose angles are 30, 60, 90. The lengths of the sides of a 30, 60, 90 triangle are in the ratio of 1 is to square root of 3 is to 2. We can also recognize a 30, 60, 90 triangle by the angles. As long as we know that one of the angles in the right angle triangle is either 30 degrees or 60 degrees, then it must be a 30, 60, 90 special right triangle. A 30, 60, 90 triangle is a right triangle with a measure of 30-degree angle or 60-degree angle and must be a 30, 60, 90 special right triangle. A 30, 60, 90 triangle is a special right triangle with angles 30, 60, and 90. The lengths of the sides of a 30, 60, 90 triangle are in the ratio of x is to x square root of 3 is to 2x, as what I have mentioned a while ago. For example, find the lengths of the hypotenuse of a right triangle if the lengths of the other two sides are 4 inches and 4 square root of 3 inches. We have to test the ratio of the lengths to see if it fits the x is to x square root of 3 is to 2x ratio. So we'll have 4 is to 4 square root of 3 is to blank is equal to x is to x is square root of 3 is to 2x. Step 2, yes, it is a 30, 60, 90 degree triangle for x equals 4. Then we can now calculate the third side. 2x is equal to 2 times 4, that is equal to 8. Therefore, the answer, the length of the hypotenuse is 8 inches. Find the lengths of the other two sides of a right triangle. If the length of the hypotenuse is 8 inches, and one of the angles is 30 degrees. Step 1, this is a right triangle with 30 angles, so it must be a 30, 60, 90 triangle. We are given that the hypotenuse is 8. Substituting 8 into the third value of the ratio, x is to x square root of 3 is to 2x, we get that 2x is equal to 8. Therefore, now x is equal to 4. Substituting x equals 4 into the first and second value of the ratio, we get that the other two sides are 4 and 4 square root of 3. Therefore, the answer, the lengths of the two sides are 4 inches and 4 square root of 3 inches. Moving to lesson number 5, which is all about trigonometric ratios. The trigonometric identities are equations that are always true for right-angled triangles. So using the illustration, as we can see, we have the theta, and the side of the triangle opposite the theta is what we call the opposite side, and the side near the theta is what we call adjacent. And then the side opposite the right angle is what we call the hypotenuse. So the same way, if the theta is moved to the other angle, let's say on the upper part, so this side is what we call the opposite, and then this side near the theta is what we call our adjacent side, and of course the side opposite the right angle is what we call the hypotenuse. Okay, same way, so this is the opposite of the right angle is the hypotenuse, and the side near the theta is the adjacent side. Adjacent is always next to the angle, and opposite is always the opposite of the angle. So solving sine, cosine, and tangent, the three main functions in trigonometry are sine, cosine, and tangent. They are just the length of one side divided by another. So given here the illustration, theta, the formula for sine theta is equal to the opposite side divided by the hypotenuse. Cosine theta is equal to the adjacent side over the hypotenuse side, and then tangent theta is equal to the opposite side over the adjacent side. Cosecant, secant, and cotangent. We can also divide the other way around, such as adjacent over opposite instead of opposite over adjacent. So using the same illustration, we can have here cosecant function of theta. Cosecant of theta is equal to hypotenuse over opposite. Secant theta is hypotenuse over adjacent side. Cotangent theta is equal to adjacent side over the opposite side. For example, find the value of the missing side of the right triangle and the 6 trigonometric ratios of theta given the figure. So we have 16, 24 theta given. So step 1, we need to solve for the measure of the third side, which refers to this side. So using the Pythagorean theorem equation, we have a squared plus b squared equals c squared. Of course, the c is the longest side, which is 24, and we will let a and b the shorter side. So we have a squared plus 16 squared equals 24 squared. Getting the value of a squared, so we will have a squared plus 256 is equal to 576. So to solve for a squared, we need to take 256 from both sides. So we will have a squared is equal to 576 minus 256. So a squared is equal to 320, and to get the value of a, we need to get the square root of both sides. So we will have a is equal to 64 times 5. So a now, by simplifying, is equal to 8 square root of 5. So this is the value of a, 8 square root of 5. So this is b, 16, and c is 24. So this is the illustration. Step 2, solve for the ratios given with the sides or the opposite. Opposite side is equal to 8 square root of 5, which is the value of A. Adjacent side or the side next to the theta, we have 16. And then hypotenuse, which is the longest side, with a value of 24. Okay, so we can now solve for sine theta with the formula given a while back. We have the opposite side divided by the hypotenuse. Our opposite is 8 square root of 5. Our hypotenuse is 24. So that would be equal to square root of 5 over 3. Solving for cosine theta, we will have the formula given a while back. We have the adjacent side over the hypotenuse side. So our given adjacent side is 16 and our hypotenuse is of course 24. So simplifying, we will have cosine theta is equal to 2 square root of 2 over 3. Moving to the tangent function of theta, we will have opposite over adjacent, and our opposite is 8 square root of 5, and then our adjacent is 16. So simplifying, we will have square root of 5 over 2. The next function is the cosecant theta. The formula given a while back is the hypotenuse side divided by the opposite side. Our hypotenuse is 24. Our opposite side is 8 square root of 5. By rationalizing, we will have 3 over square root of 5. By rationalizing, we have 3 square root of 5 multiplied by square root of 5 over square root of 5. That will give us the value of 3 square root of 5 over 5. So the value of cosecant theta is 3 square root of 5 over 5. Next to cosecant theta, we will now discuss secant theta. Secant theta, with the given formula, hypotenuse side over adjacent side. So we will have 24 as our hypotenuse and our adjacent side, which is 16. By simplifying, we will have 3 over 2. Solving for the last function, cotangent theta, we will now have adjacent side over the opposite side, and that is equal to our adjacent side is 16, our opposite side is 8 square root of 5. Okay, that will give us simplest form 2 over square root of 5. By rationalizing, 2 square root of 5 times square root of 5 over square root of 5, that will give us 2 square root of 5, or 2 times square root of 5, that will give us 2 square root of 5, and then square root of 5 times square root of 5, that will give us 5. So the value of cotangent theta is equal to 2 square root of 5 over 5. So that would be all for my discussion. Thank you so much. But of course, let me share with you my references. As you can see on the screen, we have Pierce Rod, 6 May 2019, all about Pythagoras theorem, math is fun. Or simply search for www.mathisfun.com. I also included information from www.onlinemathlearning.com.